Just कर रही मैम ही कर रही चलेगा ये साइड में ना मैंने
हेलो हेलो चली तो जाएगी बट ऐसे कर लूंगी फिर इसके कल कल ना माइक यहाँ था बीच में क्योंकि लैपटॉप नहीं था मैम एक्चुअली बट फिर यहाँ से हिल जाएगा प्रॉब्लम ये है ये वाली वायर चल जाएंगी पर यहाँ से
Everyone, please settle down quickly. Yes, all of you, please sit. Please take your seats immediately.
A very good morning to all the distinguished dignitaries on and off the dais, respected faculty members, esteemed researchers, industry professionals, and our dear friends. It gives us immense pleasure to welcome you all to the 16th International Conference, Confluence 2026, organized by the Department of Computer Science and Engineering, Amity School of Engineering and Technology, Amity University, Uttar Pradesh, Noida. Before we proceed further, please allow us to introduce ourselves. I, Kamakshi, and it is my privilege to co-anchor this session.
And I'm Ashnika, and together we'll be guiding you through today's proceedings. Over the years, Confluence has grown into a globally recognized academic platform, bringing together academicians, researchers, industry experts, scholars, and students worldwide for meaningful knowledge exchange. As a leading global university, Amity remains committed to providing a strong academic foundation and fostering research driven learning. Conference 2026 aims to foster innovation and interdisciplinary collaboration by providing a platform where theory meets real world applications.
Knowledge grows when it is shared, and wisdom multiplies when it is exchanged. Today, we are privileged to hear from four eminent keynote speakers, distinguished experts, and thought leaders whose contributions have significantly advanced research, innovation, and practical applications in their respective domains. Their insights and perspectives will undoubtedly enrich our understanding and inspire meaningful academic and professional dialogue.
We take this moment to formally welcome our esteemed guests whose presence today truly honors our campus, who have kindly spread time from their busy schedules to join us. Today we have with us Professor Dr. Seng Swan Shu, professor in the Department of Electrical Engineering and Computer Science at Florida Atlantic University, USA, Professor Dr. Ramzi A. Harati, Associate Professor at Computer Science in the Department of Computer Science and Mathematics at the Lebanese American University, Beirut, Lebanon. Professor Dr. Ankit Agarwal, Research Professor in the Department of Electrical and Computer Engineering at Northwestern University, USA. Professor Dr. Hussein Mehdi, Lecturer in the Department of Computer and Software Engineering, College of Engineering, University of Diyala, Iraq. We welcome our esteemed speakers on the panel here with us today. Now, let us understand the expertise of our panel. Our first keynote speaker, Professor Dr. Seng Zwan Shu, is a professor in the Department of Electrical Engineering and Computer Science at Florida Atlantic University, USA. He received his PhD in computer science from Fudan University, Shanghai, China. His research interests include data mining, machine learning, multimedia systems, bioinformatics, with a strong focus on big data analytics and network representation learning. Dr. Zhu has made significant contributions to these areas, representing learning through high impact research and scholarly publications. In recognition of his outstanding contributions to data mining for big analytics and network representation learning, he was elected as an IEEE Fellow, class of 2023. He will be delivering his talk on AI for the ocean, deep learning, and visual language models for manatee conservation.
Thank you. Can you see my screen now?
Yes, sir, we can see that.
Uh, Before I start, I also wanted to know how much time I have. I noticed we're about 30 minutes behind. Do I still have 30 minutes? How long do you expect me to complete? Sorry, can anybody answer me? Because I need the timing so I can decide how much time I spend.
Uh, so we can wind up the session in half now.
What?
We have around about 20 to 25 minutes. Sorry
Okay,
for the
so
delay, sir.
yeah, that's fine. Okay, thank you. Let me see. Still okay. Let me sharing my slides. Okay, so I will try to be a bit quick and with respect to my presentation. Thanks everyone. Like I said, I was not able to get my visa on time, so uh, I have to deliver the keynote in online fashion. Uh, from the introduction, actually primary of my work is on the data mining, machine learning, AI, and several most influential work would be the big data, network representation learning, some of those works. However, I think in the past conference I organized, attended, I often get most benefit from speakers from outside of the domains. Therefore, I'm actually trying to have this keynote to focus on something beyond the computing or computer science type of research. It's more focused on how does this AI to bring the social benefits. We recently received one research project from the National Science Foundation is to use AI to benefit the conservation study, and we use the manatee as the subject for our study. So I'm going to talk some of our works related to how do we use AI to benefit the environmental science conservation study, and we're going to focus on two main tasks we're dealing with. One is for the counting of the manatee, another one is to do the trackings. Many of you actually are probably not aware a lot of this critical environment we're facing. Roughly, we have about 8 to 100 million species, including plants and animals on the planet. However, there are about 15,000 are threatened with extinction, and the rate is actually very, very alarming. There is about 50 to 150 species which are extinct every single day. For that reason, the conservation study actually is very, very timely. as you will see, there are a lot of human labors involved in this because you have to go to this field and collect all the information. So what we try to do is we try to use AI to help out this whole process. Why we study manatees? Manatee are, especially Florida manatees, are very adorable animals. In total population they have is very limited. In the 2021 and 2022 survey, there are about 10,000 manatees in total spread across the east and the west of the Florida. And their mortality, which is the fatal damage to them, actually increasing because of the boating, starving, for many things. We will see in 1 year they have about a loss of the 10% of their populations. They are giant. They are typically weight about 1,000 to about 3,000-5,000 pounds. It's about 1 tons because they are in the river, so you don't notice. And they have a lot of like our mammals, especially their flippers, very much like human hands. This slides shows you the mortality of the manatee. We know they have about 10,000 in whole population, but in 2021, this year alone, about 10% of the population was dead. The main reason is starving because the red tide for that year, there is algae blooms, which are some kind of damage, environment damage, which have, they are eating the seagrass. So if they don't have enough food, they are starving. So our main goal is how can we use AI to benefit them? What is the task we are dealing with? Is we are dealing with the task of the counting as well as the tracking. Now the manatee is actually animal migrating. In the winter time, they come more close to the South Florida because they are warmer. In the summertime, they spread out, goes to the North America, like Virginia, they travel there. In some cases, the actual loudest manatee, one appeared in Florida, and then later on they appeared in the Mexico. So how does the animal actually travel there? We don't know. And the other fundamental question is how do you know the animals appeared there and in Florida are actually the same animal? The answer is the scientists use those markers to denote. Later on, when we do the tracking, you will be able to see it. So that is the reason we know it's the same manatee. But the problems we try to do here is, can we count manatees in a more computational way? That is the task. So the issue here is, why do we count a cluster or aggregation of the manatee? Manatee, as we said, they always seek warm waters. When the temperature is hot, like summer, they spread out, they don't gather. But when the temperature is getting lower than 20 Celsius, which is 68 Fahrenheit, then they will have to seek warm water. There are two warm water resources. One is a spring, which is like here you will see the pond with warm water coming out of the earth. Another one is a factory. Here you will see the plant. They have a discharge of the water. Then you will see a school of the manatees was living there. Now the issue here would be, first is how do we know how many manatees presented where? This is actually enforced by the law. In the Florida, we have a state law says when you have manatee presented in your premises, which is in your park, in your campus, in your area, you have to count them. Therefore, the counting requires by the law, and there are most recent way people are doing it is by a human labor, which is people will actually going outside of the river to look at the population and then take the survey and count how many presented. Of course, there are other way. For example, you will see there are GPS, which is tagged to the tail of the manatee. Actually, you will see this is the mother and this is the calf, which is the baby of the manatees. And the disadvantage of this way, which is more computational driving, would be the GPS tag has to be released after a while. And in the meanwhile, this often causes the tangling because if this is the long rope, if this one tangle the water bed, the trunks of the trees or other type of the structures, the manatee will be starving to death. That is the main reason we will try to use a computational approach to do it. Now, what we are using here is because the surveillance camera is actually readily available in the state park. What we will be able to do is we collect surveillance video and then we will see, are we able to just use AI to look at those scripts of the images, and then we will immediately know how many manatees presented in that area. This is very, very timing because we can immediately get a result. We don't rely on the labor. We don't rely on the weather. So we will be able to get real-time feedback because the surveillance video was already there, and this make it very, very affordable in terms of the cost. Now, the fundamental question, now we going back to the computer science or the AI side would be how do you count the objects, which is manatees here, right? One way we do the counting would be we first do the segmentation, which is we're going to segment these manatees. We segment these manatees, and then after we do the segmentation, we're counting how many objects is there. But this becomes difficult. The reason is, for example, you see these slides. This is the manatee you probably can see, but what about here? Do you see the manatee here? And what about here? You see manatee here. And there are water body with a lot of reflections, and the wrinkles make it counting very, very difficult. Okay, second way of the counting, we do it is more like a human way. When human being counting the object, we don't typically do segmentation. We don't recognize them first. We are getting the idea about what you are counting, and then we matching things by overall shape, which is we are trying to matching them and then disregard everything else and then do the counting. Now, that would boil down to how do we train AI model to do this type of the counting, right? When we train the model, we have to teach them. We teach AI by giving the label information to tell them what we are looking at, right? So when we do the labeling, there are multiple ways to do it. One way is we are using a box to highlight, says this is the manatee, this is the manatee. I'm going to count them, and then we teach AI to learn how to do that type of the counting. Right, this is more accurate but very detailed because it requires a labeling, which has a lot of human efforts. So what we proposed first is to teach the model would be we simplify as a line segment. When you see the manatee, use a single line to actually mark it. We teach AI about the several 700 of such image frame, which will be able to get a sufficiently good result. Another one simplified by line would be put a dots. Now, when you do the dots, it's easier because you don't need to bend the line to show the object. However, the dots typically give you much less accuracy about, for example, orientation of the manatee, you don't know. The overall shape of the manatee, you don't know. Of course, the most rough human knowledge we provided would be we only give you a number. For example, here we said there are 21 manatees. That type of learning is more difficult for the AI models. So in this case, our work we try to do is we try to save human labors, but also try to get the accuracies. Next question we wanted to do is assume we are able to do such type of the labeling to teach the AI model, but how do you convert such type of labeling as a counting task? This is what we call the crowd counting. We convert an image to a density map. What does density map mean? For example, if you put a dot here, and this dot will be converted from the images, goes to here, shows the density. The density map ignore anything else, only focus on what you marked here. Here I mark a dots, so the dot will be converted and remain in the density map. Everything else is going to be disappear. In this case, you consider this is the white space. How do you know how many dots inside this image? All you do is, this is your density map. You go through all the position where I and j are the width of the images, the height of the images. Sum them up. If this equals to 25.5, then you will say, okay, there are 25.5 dots or the manatees. Now the issues with such type of the approach is they does not consider the shape, which is oval shape of the manatee. So what we proposed here in our work, we propose an anastrophic Gaussian kernel. We know Gaussian kernel is kind of this type of the structure. This is Gaussian kernel, right? Now the anastrophic Gaussian kernel allows us to control two dimension. Here, you will be able to have a sigma k, which control two dimension of the Gaussian directions. In our case, we will be able to spread out one direction, second direction of the Gaussian kernel, and those sigma value, which is the standard deviation of the Gaussian kernel, we will be able to learn them. And once we learn this type of the Gaussian kernel, then our problem becomes if we have a labeling of this manatee, for example, this is the labeling of the manatee, right? Then we will be able to not only use the dots, but convert this density as a kernel density map. Then we doing the same type of summation, we will be able to get a more accurate results. Okay, because of time, I'm going to jump because you can always go to my paper to read and know the details. But here I can show you the result. For example, from the left to right, you will see the manatee with increasing number. Here you will see there's a ground truth. 2, 4, 7, 11, 27, 42. And this one uses this is the ground truth, which means they are not calculated by the AI. They just use the ground truth to show the result. This is calculated by the AI. You will see when the number is large, it's a bit of off. Here, the absolute difference is 7. But this is our method. We are using the anastrophic Gaussian kernel. You see here, when the number ground truth is 42, and then we actually get 40, the MSE, mean absolute error, is far less. More importantly, if you look at here, this is the ground truth shape of the manatee, and what we are able to see the shape here is, you will be able to see, especially here, you see the very, very nice shape, right? But our learned shape is very, very similar. Like here, this is a ground truth shape. This is what we have the first shape. So this is the result we have. I can show you the result. On the left, you see the live image. On the right, you saw the density map. As I said, you add up all the points. This will give you the numerical number. This is the counting. You see, this is the school of the manatees, about 11. And most one we encountered is about 40 something to 50 something within the camera view. Okay, this is the one you have. So this result is much more improved, and we also applied this to count the corpse and also the whales. You will be able to apply the similar approach to do the counting. Now the extension we have for this after we do the crowd counting is we actually use this for the vision language models. So we are using the crowd VRM R1 models. And what we are trying to do is we know the LLM, we will be able to give them prompting and then ask them to do something. For example, we said, please count the number of lambs or the sheep inside this image. And then you need to output the thinking process, which means we only use the chain sort, this type of the counting, and then ask them to out the number. Now, currently, the LLM, like most of the VRM model, they will be able to give you some answers. For example, they have output 1 to indicate there are 20, and then they will explain how I get this 20 number. Output 2 will give you 24, which means they have different way of counting, right? Output of the nth counting give you the 21. Now, after that, the LLM allows you to interact with them to have this counting to be optimized, and this optimization currently we use the one, which means other research also using is called the GRPO, called the Group Relative Policy Optimization. What they do is you have ground truth number. For example, I know here the ground truth is 22. If the ground truth number is 20, we find the difference, and then we see this number whether it's less than a threshold. If it's less than a threshold, you use 1, other one use 0, and this is going to be your loss. Once you have the loss, then you're going to have the gradient to propagate this theta, which will be able to return back to modify how this different way of the counting is used. And then that is the existing method for the GRPO approach doing this counting. What we did for this part is we are not using this type of the policy, and we are actually using a fuzzy way where in the original, this loss is a binary, right? We are now converting the loss into a fraction number. This fraction number is decided by both the layout, which is how you output the result as well as the number. As a result, our modification, you will be able to see here, if you have FR, that would indicate we are using this fuzzy loss to decide what is the number of objects within the scene. We use this to count it. For example, here is the drone images. This is the surveillance videos, and this is also the surveillance video in the highway. And we also do in the out of domain, which means when we do the learning here, this learning pipeline, we do this learning pipeline, we never use the manatee images, but we use manatee images in this case. So the one use our fuzzy policy, the overall performance is considered the MAE and RMSE is far better. So this one give us the motivation sets. We can train our model to do the counting. In the meanwhile, we can also use LLM, or especially those vision natural language models, with our rewarding process to actually make them better to do the counting. Now, let me use about 5 minutes to wrap up the tracking of the manatee, which is the ongoing research we did. So once we did the counting, right, and then we know how many manatees in the area, now the next question we wanted to know is where manatee go? When we say where our manatee go, we have to track the manatees. As individual manatee, you go here, there, 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 we have to track them. So we wanted to have more detailed understanding about the health behavior of the individuals. We have to track them. How do we track them? As I said, the researcher, especially those from the environmental science, and like in the Florida, they maintain a MIPS called the Manatee Individual Photo Identification System. Whenever they encounter manatee, they take the photos and then they will convert this image into some markers. So how do they convert this into the marker? This is going to be the marker. What they have is they have manatee images taken, then somebody will manually says, okay, there is scars, then we're going to mark the scar into the sketch. Now we become a sketch image. They maintain about 500,000 of those images. Then for matching, which we know whether it's the same manatee or not, what we're doing the matching is we're actually matching those markers. This process is very labor intensive because you think about it, you have 500,000 images. You find out which one is the same manatee is very, very time consuming to do the matching. And it's very inaccurate. I will show you why. And the most difficult one is the scars of the manatee changing, because if they have a scar, they heal. Like we have a cut, our body will heal, right? And in the meanwhile, when the 8 years go by, and with those algae on the body, they cover. So there are a lot of things to make this change. And in the meanwhile, when we encounter the manatee, we actually taking them. Manatee do not follow your order. We cannot even touch them by law. So in this case, you take the photo in this way, you take the photo in this way, and this way, and this way. These 4 of them actually denote it's the same manatee. Now you can find out the marker showed up in the photo in a different way. That means use classical image-based retrieval does not work. Here we show you these 3 sketch is the same manatee. This is also the same manatee. Now you can find out the difficulty here is we have a variety of the form. There's no standard way to tell us as how the marker looks like. they can be any arbitrary way of a marker. If there is this type of shape, it typically means the bolt cutting the back of the manatee. That's slightly easier to figure out. But the shape like this, typically it's called a winter stretch, which means in the winter time, and the body was slightly change and stretch because of the cold. And those can be any type of shape. So we have to use AI to do a better detection of the marker for the matching. Now, most of the researchers in the computer science would say this is easy. We just use edge detection to find out those edges and then to match like fingerprint matching. However, I show you this result. When we use edge detection, those edges, which is highlighted in color, typically does not continuous. So you don't even know that's a marker or not. Sometimes they focus on the body shape. Sometimes they focus on the nostrils. But our focus are the markers because those are the unique identity of the manatees. What our solution do is we propose to use region-based CNN, which we will be able to input this sketch into the trained model. Then it will output this marker with the bounding box, and we also know the position of the markers. Then we will try to do the matching. However, the difficult part here is, although as we said, is this is the same manatee, but when we have people converting this image, if we go back here, we said we have researchers to have look at the images and then to put a marker here. When different people, oh, it's the same researchers, look at images different time, they are putting the marker into different position. For example, this marker was marked here. This marker was relatively close, but look at this cut. It's this cut. It's the same cut, but it's the healing, which is later on the marker slightly disappear. And there are emerging of the new markers. There is also the emerging of the new markers. So that make us very difficult to say, when I give you some markers, can you retrieve whether it's the same manatee or not? What we proposed is we propose a deep learning framework, which we fine tune RCN model. This is we train a RCN model, we fine tune it. Then we have our sketch images all converted into a marker database. So now in this database, we only have markers, which means we only have those markers. Then when we have input images, this is the input for query. We convert this, use the trained RCNN to get all the markers. Then we compare marker to markers to find out which one is more similar, and then bring the most similar one to match the query. Of course, there are more detailed challenges. For example, when the marker at a different position, how are you going to do it? And then when we have two sketch images, the marker are not same, even in the number are the same. So how are you dealing with? But overall, we overcome those challenges, and then we come up with very good result. We compared with general deep learning method, most of simple image processing method, the performance are actually very, very well. So this result actually draw a lot of attention worldwide. Our work was covered, I think, in more than 20 news channels worldwide, including I know some of those reporters from Indian news media also covered us. This is about our matching for the manatees stretch. So with here and the timing, so I will stop here. And I think my focus is try to emphasize on how do we use AI to benefit the protection of our Earth. And this is the part I think less monetary driven, but more impactful for your research work. And hopefully we will be able to contribute and use AI to benefit our society. And any questions? I'll stop here. Any questions?
Yes. So any questions, students?
if I know we have a very strict timing, if there is no question, I think a student can either send me an
Questions?
email and yeah, go ahead. Yeah, if you have some question, you can send me through email. I think if you have interest to work on this type of research, you can contact me and I will be able to try to accommodate. Uh, so we have source code, we have data, and we also publish our GitHub online, and all of them, especially for the first counting of project, you can find data online. Yeah.
Thank you, Dr. Zhu, for such an insightful and thought provoking address. Our second keynote speaker is Professor Dr. Ramzi A. Harati, an Associate Professor of Computer Science in the Department of Computer Science and Mathematics at the Lebanese American University, Beirut, Lebanon. He holds a PhD in computer science from North Dakota State University, USA, and earned his PS and MS degrees from Minnesota State University. His research interests include database management systems, machine learning, and multi-level secure systems. He serves as Secretary General of the Syndicate of Computer Sciences in Lebanon, Commissioner for CASAB EBET, and Vice Chairperson of the Arab Computer Society. He is also an active member of the Association for Computing Machinery.
Both of them work? Okay. So good morning to you all. In the interest of time, basically, I'm just going to start talking to you basically about cybersecurity and how it affects basically information systems. In particular, basically, we're just going to shed some light on healthcare information systems, what happens basically when somebody attacks your database, and what do you do about it, if you will, basically. I'm not going to go over my background. You know, somebody just basically talked about this. But I'm going to tell you a bit about, my affiliation with computer security and how this work all started all together. So just to, put some background into the topic itself, if you will, basically, that computation has been around for over 80 years. We saw that first computing systems basically were actually invented in the 1940s, back then, if you will, basically. And when they were invented, basically, there were no security actually intact. So everybody wanted to use computing systems because they were extremely expensive. So for a number of years, for a number of decades, as a matter of fact, basically, nobody actually treated security with any sense of responsibility, until basically the US government started thinking about basically deploying computer system in their particular, environments. We're talking about the US Department, of War. Now it's actually called Department of War. Back then it's actually called the Department of Defense. So here comes the 1960s era, if you will, basically. So in the 1960s era, if you will, basically, NSA, which is a branch of, the US government, if you will, National Security Agency, stipulated, hey, enough actually with not having security. Let's actually think about having a methodological way, a standard way, not an ad hoc way, basically, but a serious way about basically tackling security. So what they did during the 1960s and 70s era is that basically they formed something which is known as Tiger teams. And those are actually mathematicians whose sole job basically is to look at computing systems and figure out basically whether we can penetrate these computer systems or not. So this was done ad hocly. not systematically, but ad hocly. Put a bunch of people in a room and figure out whether you can particularly hack a particular system or not. So that went on basically through much of the 1960s and 70s. And in the 1980s, the Department of Defense said, enough of that. We need a better way basically to deal with security. Okay, so what they did basically in the early 1980s is that they established something which is known as the National Computer Security Center, which is a center that belongs to the National Security Agency in the States, if you will, basically, whose main task is to look at computing systems and figure out a standardized way to evaluate them to ascertain basically that they are of high caliber in terms of security, if you will. So in order to do that, they established something which is known as TCSEC, which stands for Trusted Computer Systems Evaluation Criteria, which is nothing more than a set of criteria and a set of standards and a set of assurances to ascertain, for instance, basically like Microsoft Windows operating system is secure. The DOS operating system is not secure. The Unix operating system is extremely secure and so forth. But in order to give them those labels, you have to have criteria. You have to have assurances, if you will. So they established basically those set of criteria. And the color of the book basically that they put them in is actually orange. So that TCSEC, Trusted Evaluation Criteria, is loosely known as the Orange Book. So this primarily, basically in 1985, targeted operating systems. Mainly basically during that era, basically Unix and Unix flavors operating systems, basically. Microsoft was not actually existing there, and there was a bit of DOS operating systems, if you will, in that era, and so forth. So soon after that, they said, well, you know what? We cannot actually work on operating systems alone. Operating systems are getting linked together because we have networks now. So soon after that, they established something which is known as the Red Book, which is basically the criteria that tailored for security for networks. Okay? It was loosely called the Trusted Network Interpretations of the TCSEC. So how do you apply security to networks? So they've added encryption, basically, and hashing techniques and so forth, basically, to the networking technology. And soon after that, basically, of course, comes the area or the era of databases. So they came up with the Lavender book, basically, which tailored for security for databases. The Oracles, basically, the SQL servers at that time, the Sybases, if you will, the Informix databases, and so forth. So they created that criteria for them. So what is this criteria is all about? This criteria basically looked at security in terms of 4 divisions: the A division, the B division, the C division, and the D division. Okay, of important security aspects. In other words, basically going upwards, every system by default fits the D division, meaning basically it's not secure at all. But as we go upward the hill, basically into the C division, into the B division, and into the A division, we get more and more security. As a matter of fact, basically at the A division, at each one of those divisions, they basically categorize them into classes. The A1 class, for instance, basically the B3 class, B2 class, B1 class. At the C division, there's 2 classes, C1 and C2. And as you go upwards, basically, you get more and more security. The most secure system that is actually out there will get an A1 labeling, meaning that it is mathematically proved to be secure. And imagine that, mathematically proved to be secure. In other words, basically, if you have a system that is made up of tens of millions of lines of code, you have to mathematically ascertain that it's actually secure, not by just testing it, but by mathematically proving it's actually, and it's very a complex task, if you will. Much of the secure systems basically fall into the B division, if you will, at the B1 level and the B2 levels, if you will. Okay, so at that era, if you will, basically, since nothing was actually secure, and I was actually involved with that particular security aspect during my heydays back when I was working with the agency, if you will, basically, that they wanted everything to be C2 secure by 92. C2 secure means basically, much of the security aspects that you see today, discretionary access control, if you will, basically login, identification and authentication, basically object reuse, how do you reuse a memory object and the like, basically are present in C2, if you will. So what I'm trying to actually bring to your attention basically is that nowadays we talk about cybersecurity, right, and how important actually it is. But look at the dates over here. We started dealing with security ever since the late 1960s, if you will, and the 70s. Now it's actually gaining prominence, if you will. But basically, we have been tackling this issue for a long time. Now, basically, we have a plethora of software, plethora of AI that's helping us attacking systems, basically. So we need basically cybersecurity in order to actually defend the systems and the like. So in addition to those, 3 books, the orange, the red, and the lavender book, basically, the NSA, National Security Agency, said, well, let's actually complete the gamut, if you will, basically, on other things that are actually secure. So they established basically something which is known as the Rainbow series, which basically tells you how do you secure your system from an AI perspective? How do you secure your system basically from a login perspective? How do you gain security basically from a testing perspective? How do you gain security from a configuration management perspective and so forth? So they came up basically with a rainbow series, if you will, to supplement the 3 main books that they actually have there. Okay. So those set of criteria, basically, the TCSEC with its different colors, if you will, were actually termed the federal criteria. So they applied basically only in the United States of America, if you will, basically. And here comes the allies, basically, Germany, France, United Kingdom, the Netherlands, and the like. They said, hey, US, we want to be in on that pie, Why don't we collaborate, if you will, basically, so that we establish a wholesome criteria for all of us over here, basically. So originally, basically, 8 nations came on board with the US, basically, and they established an agreement with them, saying that if I take a computer system and evaluate it in Germany, it will be accepted in the USA as being evaluated as if it was evaluated in the US. And, they have a reciprocity agreement. If a system is evaluated in the US, it will be accepted in Germany and so forth. Then after that, basically, 30 other nations basically jumped on board. So we called that criteria, which was actually called common criteria, now basically became called, common criteria, with basically 30 nations actually on board. And it became part of the, ISO standard 15408, if you will. So with this criteria, basically, the main difference with it is that they don't have divisions, like the A division, the B division, the C division, and the D division. They have evaluation levels. They have 7 evaluation levels, from evaluation level 1 to evaluation level 7. And as you go upwards, basically, you gain more and more security of your particular system, if you will. And the main thing with this particular notion is that they establish something which is known as protection profiles, which is different, basically, than the original federal criteria. And the protection profile, basically, you go out to a customer, like basically an airframe manufacturer, basically, for air forces around the world, if you will, and you ask that manufacturer, what is important to you? What security profile you want to actually have? And he will tell you, I want encryption, I want basically discretionary access control, or mandatory access control, or role-based access control, or this and that, and so forth. So you build your protection profile, and then you start evaluating, basically going up the ladder, EAL 1 all the way to EAL level 7, if you will. So this is the main difference. So security became flexible depending on what the customer actually wanted, as opposed to being rigid originally, basically, as stipulated in the federal criteria. And I was, part of all of the endeavor, basically, that you're seeing on the board back then when I was working actually in the States. So just moving forward, basically, if you talk about, security, basically, the threats, to dealing with information when it comes to security are threesome. One of which basically is loss of integrity, meaning basically, your data is manipulated without your knowledge, basically without your access, without your permission, if you will. The second one is loss of availability, when somebody basically renders your system not usable because they attack you. We call those basically denial of service attacks, basically, and those are actually very dangerous because our systems now are on the net. So we are very subjective to those. And basically, in addition to a distributed denial of service attack, where basically we get attacks from a myriad of places, and therefore it's actually more dangerous. And the third one basically is loss of confidentiality, meaning basically, we'll allow our users to read our data without our permission. And that's basically dangerous as well. So those are the 3 tangents, basically, or 3 threats of information, if you will, when it comes to security. So what do we need to do with regards to those, basically? So when I have an attack, basically, I did not do that. That's not part of the presentation. I promise you. Is that normal? Oh, okay, so we pause. Okay, sure. So thank God for phones, right? Basically, we can use some lights using the phones. Sure. Is that usually fixed? Is that fixed immediately, or that takes a while? It depends.
Question. As you were explaining regarding the A1.
Sorry?
As you were explaining regarding the A1 security protocols that we are using.
Sure.
Sir, as we are moving with the AI, what I feel is cybersecurity moves hand in hand. Okay. So as the AI develops, cybersecurity will be needed more. And
Right.
so how do we are working upon the futuristic threats that are coming? It's a few days ago, I read an article in which it was explained that an AI model cracked the highest security level of a firm. So how do we are developing that A1 model so that we can get more secure?
Right. So right now, there we go. Can I do that after the presentation? We can have a discussion afterwards, okay? Remind me.
Sorry for this.
So, wait. So do you think this is a security attack here, or? So we need to recover from it, right? Basically. Very stick, take a while to warm up, yeah, the lamps. All right. So we left off by basically saying that once we figure out that there's a threat to our information from an integrity perspective, from a denial of service perspective, from a confidentiality perspective, our main thing is basically to recover from those attacks as soon as possible, if you will. And this brings us basically to the notion of information warfare, which is basically pretty prevalent in this day and age, if you will, basically. So information warfare is the notion that, you have yourself and you have basically an adversary, if you will, basically. The job of yourself basically is to attack the adversarial information base and render them useless so that your adversary would read the data and make bad decisions because you mucked around with his or her data. Okay, so you want basically to put him at a disadvantage by mucking around with his or her data. And that's basically the notion of information warfare that we're seeing actually all over the world, if you will, basically. So nowadays, if you will, basically wars are not basically fought on the battlefield with tanks, with airplanes, with ships and the like. They're fought basically by manipulating information from one country to the other, from one particular agency to the other, and the like. One of the biggest examples, I should say, basically, of information warfare happened basically a few decades ago, and that was the grandest scale that we saw basically in information warfare. This was actually during Desert Storm, which is the war between Iraq and Kuwait. And in that particular era, if you will, basically, Iraq was a humongous country as far as an army is concerned, the fourth biggest army in the world. They had like basically 3 million soldiers. They are armed to the teeth, if you will, basically. They took Kuwait by surprise, and they just occupied the entire country. And here comes basically the allies. If you basically, they formed, I think basically at the time they were 48 nations. If you basically, they got together and said, well, we need to, liberate Kuwait, So what happened basically is that, and this was led by the Americans, of course, basically. So what happens is that they actually did information warfare attacks. They mucked around with the information bases of the Republican Guard of the Iraqis, if you will. They manipulated their information. They did a lot of basically jamming of their signals. They basically did power outages in order to. So this was a slide switch. So I'll continue with the story, if you basically until we get the slide, until the system is back on again. I'm sorry.
Weather is wet. There's the rain.
Sure.
There might be outages now.
So this is off again. Is it going to be automatically on again? Thank you. Do you want to turn this back on again, or is it turned on automatically? Okay, there we go. Sorry? Sure. So basically, yeah. So they tricked the Iraqis, telling them the attack was going to be on Iraq from the south, from where Kuwait actually is. But basically, the attack came from a left hook, basically came from the Anbar province, basically through Saudi Arabia all the way to Iraq, and they basically left hooked them, if you will, basically, and liberated Kuwait and so forth. But the point is that this is the first ever, basically, information warfare that was conducted on a large scale, if you will. I was going to show you another example, if you will, over here. Scaling down basically to our systems that we deal with on a daily basis. So if you consider, for instance, a medical healthcare system, if you will, so the medical healthcare system, if you will, would store a lot of information about patients, right? Patients' health records, their private information, basically their statuses, they're sick, they're ill, or whatever, basically past surgeries, and so forth. So what happens? I'm just going to continue with the slides and just tell you the story over here, basically. What happens if that particular medical database gets attacked? If you will, basically, somebody basically would come and alter the records. So this database basically may have a lot of false information, bogus data, deleted data, altered data, inserted data, if you will, basically. This would render your information system actually useless, right? It would render it useless, if you will. And therefore, basically, the database, if you will, should be isolated, because it is catastrophic, if you will, because it contains a lot of bogus data. So this particular type of attack may result in many things, one of which basically is a denial of service, because basically, the data is no longer valid, no longer may be available basically to users to use. It may be actually lead to exposure of sensitive information. So for instance, basically the status of a patient, whether for instance he has or she has basically cancer or not. It may actually lead to health complications. If you alter the dosages of medicines basically to a particular patient, that basically may lead to problems, if you will. And worst of all, basically, is actually it may cause a person's death because you alter the medications in such a dosage that it causes them basically to die, unfortunately, if you will. So you may think that this is far-fetched. No, it's not. Consider this case actually in Germany. We have a nurse whose name is Niles Hogel, if you will, basically. Niles Hogel went into databases basically and altered the dosages of patients basically so that they undergo cardiac arrest. And once they undergo cardiac arrest, basically, they would call on this guy, on Niles Hogel, if you will, to resuscitate them. He loves to do that job. He was actually coined Resuscitation Rambo because he loved that particular effort of reviving people and the like. Unfortunately, basically, Niles Hogel, by his alteration of medication to those particular patients, may have killed actually upward to 300 patients over a number of years. And Niles Hogel, basically, who's in Germany right now, basically, behind bars, he's serving basically multiple concurrent life sentences of the deaths he actually caused. And the number, basically, of deaths are actually rising, right? Basically, because they go back in history, when did he start, what did he do, why did this patient die, and so forth, basically. So these things basically can happen in real life. And this is the biggest case, basically, of altering of information that basically led to the loss of life. So when we have things like Niles Hogel, basically, what we need to do is actually try to expedite our recovery. First of all, basically, we need to stop Niles, in his tracks. But if we fail to do that, we need basically to figure out what is the best way to actually, recover from such particular attacks so that no patients can actually die. So here we have basically the pillars of information warfare, which are, again, threesome, one of which basically is prevention, meaning that if an attack takes place, we need to prevent it in its tracks before it's actually happened. So that's why we have fireworks and other, type of, methodologies and the like to stop attacks in the first place. But we all know basically that security is not 100% guaranteed. So basically, we're going to lose power again. So basically, if prevention does not work, basically, we move to the next stage, basically, which is detection. So if an attack, falters through the wall, if you will, basically, if an attack happens, we should be able to detect it, right? Basically, and here comes the job actually of intrusion detection systems. And nowadays they are powered with AI to figure out basically what is the norm and what is the abnorm, if you will, basically, in order to detect such malicious activity, if you will. And once we detect that, basically, we need to actually go to the third stage, which is actually called reaction, meaning basically I have a malicious activity in my environment. How do I go about dealing with that particular malicious activity? How do I identify the damage caused by that malicious activity and recover from it, if you will? And this is actually, what we coin actually is a pseudo-random, state of actually databases. So at any point in time, basically, a database is running in a correct state. Basically, databases are responsible for moving information from one consistent state to another consistent state, basically throughout their lifetime, if you will. But if we are subjected to an attack, we actually go in a pseudo-random state, whereby basically we have to shut the database down a bit, basically, deal with the malicious activity, clean the database, and put it back actually on time again. And we need to do that in the least amount of time possible, again, basically, because time is money, if you will. Basically, the patient's lives are online, so we need to be able to cater for that. So here's basically the framework of the kind of work that your colleagues basically in my university actually did, so I'll show you what the kind of work that they carried out. But they based their work, basically, students like you basically based their work in dealing with damage assessment and recovery and all of those issues that we talked about, based on this particular framework, if you will. So we assume that the prevention technique did not work, right, basically, and malicious activity, if you will, went through. So we need to have actually an identification intrusion detection system, if you will, basically, to identify that malicious activity. And in databases, as you know, basically, that malicious activity comes in terms of programs, or rather, basically, in terms of transactions that you want to execute inside your particular system that contain operations, read, write, update, delete, insert, and the like. So this is the intrusion detection system, basically, would list for us the bad activity in the system. Hopefully, we'll capture all of them, and hopefully, we'll capture it right there and then, and not basically sometime later, because, the more you wait on capturing the activity, the more the damage will spread in your system, unfortunately, if you will. So once we actually, get the list of malicious activity, if you will, we actually need to do a damage assessment of your particular system. So those particular transactions affecting those data items, basically, and those data items were read by other transactions that caused other data items to be altered. So we have basically a dependency list of transactions on one another of those malicious activities, if you will. And once we identify those, we need to basically recover those activities by actually deleting the malicious activity and restoring the affected transactions to their previous state, their previous correct state, if you will. And then basically, we'll put the database back online actually again. So intrusion detection, damage assessment, recovery, the database will be back online actually again. And we need to do that again in the most expedited manner possible. So students like you, basically, in their capstone years, in the final year project, basically, I challenged them with this particular issue, and they came up with various solutions, basically, to deal with it. One of the solutions, basically, is to use a matrix-based approach, whereby, basically, the matrix contains a list of transactions that are almost serially listed one after the other. The correct term for them basically is known as rigorously serializable, but rigorously serializable fashion is almost the same as a serial fashion, So transaction 1, transaction 2, transaction 3, transaction 4 come into existence, basically. We list them one after the other, if you will, basically, but not exactly serial, almost serial, if you will. And on the top over there, basically, we have a list of data items in your particular database, wherever those data items are, records, tables, table spaces, whatever your granularity of data actually is, if you will. And then those transactions would contain basically bits of zeros and ones, basically, and some other factors such as basically a transaction ID that you see over here. So zeros basically means that the transaction never touched a particular data item, okay? Never touched it, basically. One means basically they touched it, they clamped on that particular data item. Positive transaction ID that you see over here basically means that the transaction basically read this data item and based on that reading, changed the data item, modified it, if you will, basically. And the negative transaction ID that you see over here means that that transaction, a particular entity, read data from more than one transaction, So transaction Y, read data written by transaction X, Y, X, T, and Z, if you will. Based on these readings, it wrote that particular data item. So we need to capture that dependency among transactions, if you will, in one another, to figure out basically how to actually assess damage in our particular system. So originally, basically, students came up with this particular model. That model basically is simplistic because it deals with arrays and it deals with bits of zeros and ones. And as you all know, basically, it is efficient to deal with bits of zeros and ones because you use logical operations, right? Basically, logical or and what have you. Then another group of students basically came and said, well, instead of using actually a single bit to represent the activity basically of transactions on these data items, let's actually use multiple bits. Okay, 2 bits to be exact, if you will. Basically, still dealing with bits, basically, it's very awesome, it's very correct. But now we have introduced a notion actually, which is very important, that transactions are blindly written. Meaning, if you have basically, a data item that is corrupt, some malicious activity came and corrupted that particular data item, and you overwrote it legally, if you basically, that helps you out because no other transaction will read that corrupted data item anymore because you erased it. You wrote it, if you will. That helps you a great deal in the damage assessment and recovery effort. And we needed a way to capture that particular notion because much of the activity basically nowadays also includes blindly writing data items in databases. You don't have to read the data item in order to write it. You just simply can write it itself. And that is actually known as a blind write. And the other, things are actually the same, the positive ID and the negative ID, which transaction basically, change the data item and which list of transactions in the negative ID fashion basically were involved in changing a particular data item. That's the second group of students that actually have worked on this. Then, to give you a model of how things actually worked for both of these particular groups, one with 1 bit and one with 2 bits, this is the example of the 2 bits, basically. So I have an intrusion detection system over here that identifies the malicious activities in our systems, if you will. So they identified, for instance, 3 transactions, transaction 25 and 28 and 33, being culprits, being bad in our system, if you will. So actually, we bring them to our particular model that we built, right? Basically, oh, short of time, okay. So I have many models. I'll just stick to this one, basically. I just wanted to show you the progression. So anyways, basically, we look at those particular issues of here. Since basically it's transaction 25, that is the culprit, that is the bad activity, we start our work basically with transaction 26. So the 24 first transactions are fine. Transaction 25, we have to delete. And transaction 26 and onwards, we have to see whether they did some work dependent on transaction 25. Okay, and basically our damage assessment and recovery process, begins from that particular notion and so forth. I'm just gonna, wind through this briefly, just tell you what other students have done. Other students actually have worked on linked lists as opposed to actually using arrays, because arrays are great, but they are sparse, if you will, basically. So this is a more, if you will, intact place. So they list the transactions and basically what are other transactions that are dependent on this particular transaction. And the third approach basically is that, I was going to spend some time on this, but we're short on time. In answer to our friend over here, basically, is that how to use AI into the current notion, basically. So we use an agent-based approach, basically, that partition data into quadrants, if you basically. And we send transactions to each one of those quadrants that are pertinent to the activity of that particular quadrant, if you will. So if a transaction, very quickly, basically, I'll highlight it in red. If a bad activity basically happens in this particular red notion over here, we shut down this particular notion as opposed to shutting down the entire database. So you're doing basically with partial shutdown, if you will. So your database and information base is actually still online. 3/4 of it online, only the red one is there until basically, we get rid of the, where's the light? Until we get rid of the bad activity basically that is listed over here. And this, I was going to spend some time over here, but anyways, just flying through those. Of course, basically with any particular kind of work, you have to demonstrate your proof of concept. So you have to do basically experimental results. And out of those, basically, the last approach, the agent-based approach, have actually worked tremendously. So those basically list the light blue, list the arrays, the dark blue list basically linked list, and in the green basically shows you how best the performance of agent-based approaches and AI. This is just to show you basically, that I have many students basically that have worked on these particular approaches. Each came up with their different contribution to the particular scheme and published it basically in conferences and journals. Hopefully you'll follow suit with your professors here, at MIT University. Of course, basically, again, performance is one side of the track. The other side of the track is memory. You have to, look at your memory footprint on systems, if you will. The blue approach over here is the worst approach, which is basically the matrix approach. The best approach is basically right over here, way down there. It consumes the least amount of memory, which is the graph-based approach. What we're currently working on basically is tackling things that are actually multi-level in nature, basically because data in secure environments tend to be classified. Some of it are top secret, some of it basically are confidential, some of it are secret and the like. How do you handle basically, occurrences when it comes to that? And basically working on current trends such as distributed systems and basically blockchain technology and the cloud and fog computing. They're all interrelated with one another actually because they're working on distributed ledgers. I'm going to stop here since I'm out of time. Thank you for your listening ears, basically. And if you're short on time, maybe you can have discussions, side discussions with you afterwards, because I have a lot of time. I'm on campus, if you will. I'm here. If you like to discuss this matter forward, let me know. Okay. Thank you for your listening attention and good luck in your careers. And hopefully we'll see your names, on publications down the road. All the best to you. Thank you.
The best way to predict the future is to invent it. Thank you, Dr. Harati, for that inspiring talk. Our third keynote speaker is Professor Dr. Ankit Agrawal. He earned his BTech in 2006 and PhD in 2009, and he is a research professor in the Department of Electrical and Computer Engineering at Northwestern University, USA, an affiliate faculty at Northwestern International Institute for Nanotechnology, as well as at Northwestern Paula M. Trenes Institute for Sustainability and an honorary professor at Amity University, India. He specializes in interdisciplinary AI, machine learning, and deep learning with a strong focus on high performance data mining and real world large scale applications. He has led or contributed to 25 plus large scale projects exceeding USD 100 million in funding from major US agencies and industry. He currently serves as editor in chief of Computers, Materials, and Continua and is recognized amongst the world's top scientists by Stanford and Scholar GPS. He will deliver his talk on AI for science and engineering, leveraging GNNs, LLMs, XAI, nano combinatorics, and more. We welcome you, sir. Guys, can we please have a big round of applause?
Yep. All right. Thank you so much. Hmm. So I appreciate the kind invitation. It's always a pleasure to be at MIT. I was here for Confluence 2020, 6 years ago, and since then I've been fortunate to get an invite every year. So I am very much grateful to MIT for this opportunity again. Um, I'll be talking today about AI for science and engineering. That's what I've been doing over the last 10, 15 years now. Uh, these are my team members and collaborators. So I'm a computer scientist by training, but I collaborate with domain experts a lot. A lot of collaborations in material science, in healthcare, in mechanical engineering, civil, and so on. So I want to acknowledge all my collaborators and all the funding agencies that have supported my work over the years. So this is, before we start, just a bit of background about the kind of work that I do and our research group as a whole. In this era of big data, I strongly believe that there are two fundamental technologies of computer science, AI and high performance computing, that need to be integrated more than ever before if you have to solve the big data challenges. So we call it AI and high performance data mining, where we take these AI algorithms and scale them and parallelize them so that they can work on big data, on supercomputers, and so on. So that's one part of our lab. But I'm personally also very interested in applying these algorithms in different real world problems, like in materials, healthcare, and social media, and so on. So today I'll be talking mostly about material science applications, so material science and engineering, and we'll see. So over the last 10, 15 years now, as I said, I've been fortunate to be part of these projects on AI for materials in the Center for Excellence. This is a $60 million Center of Excellence sponsored by NIST, National Institutes of Standards and Technology. And I'm co-leading the AI tool group in that. We are currently in our 12th year. Then an Air Force Muri project, DARPA Simplex projects, some NSF projects, Nano Combinatorics. This is a new collaboration we've started at Northwestern. I'll talk a little bit about that. And then lately, there has been a lot of interest from industry. A lot of companies have approached us to try to learn and integrate these AI techniques in their workflows. So a couple of projects from Toyota, Japan, and again, I'll give some results from that as well. So I like to start my talks with this. You can call it my pet slide. Almost 10 years I've been using this. If you look at how science and technology has evolved over centuries, not just years or decades, we can very clearly recognize or identify these four paradigms of science. So in the very beginning, science was purely empirical, right? Everything was based on observations. We look at the sky, we look at things around us, and we try to gather knowledge by perception. So that's famous as the experimental branch of science now. Then in the 17th century, when calculus was invented, we could take real world phenomena and express them as laws. Things like Newton's laws of motion or laws of thermodynamics. These are examples of the second paradigm of science, model based theoretical science. Then over time, because these are systems of equations, right? So it becomes, as they become larger and larger, it is difficult to solve them analytically. So with computers, when computers were invented in 1950s, we could solve these equations on computers and then supercomputers. So that gave us the ability to do simulations. So today we can do all kinds of simulations, like weather simulation. Here I'm giving some examples of material science simulations, like density functional theory, molecular dynamics, finite element simulations. These are some examples of computational simulations. Then over the last 20, 30 years, just the sheer volume, velocity, variety of data has outstripped our capacity to make sense of it. So even as computer scientists, we have become very good at generating data, in storing data, and retrieving data. But when it comes to analyzing and extracting insights, our capacity is very limited. So that's where this fourth paradigm of data-driven science or AI-driven science becomes important. And things like predictive analytics, clustering, all these are important techniques here. And needless to say, this is a very challenging problem, right? And I like this example of finding needle in a haystack, because needle is something that you want to find, that is the information, hidden value in this big data. And haystack is, of course, huge, and it's very difficult to find that needle. So that's definitely one point, that it is difficult to find the needle. But I like this example also because it tells us that it is easy to find the wrong needle. What that means is that if you're not very careful, if we just take some data and take some technique and try to build models without really understanding what these techniques are, what are the limitations of it, or what the data is, how it was collected, who collected it, how accurate it is. If we just blindly take some technique and some data and put it together, we will likely fall into the trap of these wrong needles. So this is very important for this field, and we'll come back to this point, that it's not just enough to apply AI blindly. You have to understand this technique thoroughly. So what is AI? Ability of machines to perform tasks that normally require human intelligence. I'm sure you have seen these kind of Venn diagrams, that deep learning is a subset of machine learning, subset of AI. And there are different ways to classify these techniques. I particularly like weak, strong, and super AI. And interestingly, all the AI that we have today is an example of weak AI. Now, what that means is that we can build an AI system which is almost as good or even better than humans for one particular task, but it cannot do everything the human does, which would be strong AI, and super AI would be beyond that, superhuman capabilities. So all these sci-fi movies that you see where AI takes over the world, that's what super AI is. Unfortunately, that's not happening, at least anytime soon. Although, if you're following this field, I'm sure you're aware that there has been a lot of chatter, a lot of voices about regulating these AI techniques, because there are fears that these techniques are becoming too powerful, too fast, especially with this generative AI over the last few years. So there is a real call to regulate the and use it in a responsible fashion. So that's a whole different topic, but I think it's important to keep in mind. Like any technique, it's a double-edged sword. So what is machine learning? the field of study that gives computers the ability to learn. So keyword is learn here from past data. And the performance of these algorithms improve as they're exposed to more data. And they have always been hungry for big data and big compute, because you see these concepts have been conceptualized back in 1950s. Again, they became popular in 80s. But only recently we got the capability of big data and big compute. And that's where deep learning comes in, which is again nothing but a rediscovery of neural networks, fueled by the availability of big data and big compute. And today, a lot of AI is driven by these deep learning algorithms, which, like any technique, has its challenges and advantages. As I said, it requires big data and big compute to make a good deep learning model. Architecture search and interpretability are also open problems in deep learning. It's not straightforward to get the optimal architecture and interpret these models. But the advantages of deep learning typically outweigh the challenges. And the biggest advantages is it is feature engineering free. So we don't need to handcraft features anymore. We can just give it raw data, like raw images, and it can figure out the features, hierarchy of features by itself. And it's more accurate and it's fast. And there are different kinds of deep learning models. Fully connected network is, of course, the traditional network with the input layer, output layer, and a bunch of hidden layers. Convolution neural networks is for image data, which provides a nice property of spatial invariance. Graph neural networks is for graph data. Generative adversarial networks is a special kind of generative network where you have two neural networks, not one, generator and discriminator, and you train them together side by side to try to make each other stronger. And then one of the latest architecture is the transformer architecture. So the T in ChatGPT stands for transformer. And because of this multi-headed attention and some enhancements in the architecture, it has been proven to be a game changer in these kind of applications. So practically, many of the models that you'll see today are either directly transformer based, or these are like using some kind of transformers as pre-trained models and so on. All the LLMs, for example, are transformer based nowadays. So coming to the focus of science and engineering, how can AI help to advance material science in this case? So I'm not a material scientist by training, as I said, but I collaborate with a lot of material scientists. And if I learned one thing from them, it is that almost everything in material science depends on these so-called PSPP relationships: processing, structure, property, performance. And this is very synergistic with bioinformatics. I did my PhD in bioinformatics about 20 years ago. So there everything is sequence, structure, function relationship, right? You start with the DNA sequence that gives rise to a protein sequence that gives rise to protein structure and then function. So pretty much all bioinformatics is revolving around that. So similarly in material science, it's about processing, structure, property, performance. And the science goes from left to right. So science is basically cause and effect, right? So processing is the cause, structure is the effect. Structure is the cause, property is the effect. So the cause and effect goes from left to right. And engineering is directly opposite of that, and it goes from right to left. So if performance is the goal, the means to achieve that goal is to work on processing, work on structure, work on composition, and so on. So I can think of it as science is the prediction problem. Prediction means that given a material, what is the property? That is the science question or the prediction question. Engineering is the opposite. Given the property, what is the material? That I want this property, what material should I have? So you can see that these are the forward problem or the science problem is somewhat easier, because for a given material, there is only one property, right? But for a given property, there can be many materials. So the inverse problem is much harder, because you want to be able to discover as many as possible or all materials that have that property. So you can select. So materials informatics or AI for materials can help us generate these forward models for predictive analytics, where you can express the property as a function of some representation of materials. And then if you have a good forward model, you can use it for inverse models, because then you can use that model to run on the entire space of materials. All possible materials you can run through that model and find the best material that you want. So that's what AI can be used for, both in terms of forward and inverse. And I explained this in this perspective article from 2016. You're welcome to take a look. Another way to look at this AI applications is in terms of, I already told you that it's forward and inverse, two kinds of problems. For the forward problem, I see two challenges: the small and big data challenge. And for inverse modeling, there are this big and huge design space challenge, because it's a question of how many possible materials are there, so that you can choose from that. And that is never small, it's always big. So if you remember periodic table from high school, anyone remembers periodic table here? There's a periodic table of elements, right? How many elements do you think there are on that periodic table? Roughly? Yeah, around. So let's say to keep our calculation simple, about 100. So there are about 100 elements. And let's say I have ternaries. So there are 3 elements in my compound and I have 100 choices for each. So how many possible combinations? Uh, how much is that? But you can repeat it. So let's just keep it simple for now. So instead of combinations, 100 choose 3, let's just do 100 time 100 time 100 to keep it very simple. So that's about a million, 10 per 6 combinations. And if you remember, it's not just the combination, it's a ratio also that matters. So like sodium chloride is NaCl in 50-50 ratio. Ferric oxide is Fe2O3, 40-60 ratio. So there can be different combinations. So if you apply all different ratios, then maybe from million, you can maybe get to billion or trillion combinations, right? So that's a big amount of possibilities, but it's still not huge. That is big. You can take an AI model and run through everything. Trillion combinations is nothing. Within an hour, you can scan through everything using an AI model. But when it comes to microstructure, your design space is huge. So 10 to the power 100 combination. So again, let's do a simple calculation. If you have a very simple microstructure, just a 2 by 2 square with 20 by 20 pixels, each pixel can be black or white. How many possible pixels in this image? 20 by 20 square. 20 by 20. So it's a 2D, not even 3D. Very, very simple. So 20 by 20 is 400. And each pixel can be black or white. So how many possibilities? So there are 400 pixels. Each pixels can be either black or white. So 2 possibilities for each pixels. So number of combination is 2 raised to power 400, because each pixel can be either black or white, right? So if you take the log and all that, you'll figure out that it's more than 10 to the power 100. So even in a very simple microstructure, the number of possibilities is astronomical. And even if you have an AI model which can predict for a given image what the property is, it will take you, 10 to the power 50 years to just scan everything. So it is impossible to do it in our lifetimes. So what can we do? So these AI techniques, there are different techniques that have been developed both from our group and elsewhere to address these challenges, both the small and big data challenge, as well as the big and huge design space challenge. And you can see that these challenges occur in pairs. So the small and big data challenge is coupled with the design space challenge. And the most challenging scenario could be when the available data is small, but the design space is huge. So that's where you need innovative AI techniques which are driven by HPC to solve these challenges. And over the last 10, 15 years, as I said, we have worked on all of these challenges. You can see this small data challenge, big data challenge, big design space, and huge design space. And we have tried to publish both in computer science conferences and domain, material science journals. It's getting good readership, a lot of software tools available, and so on. So I'll not be able to describe everything here, but just a few examples over the next 10, 15 minutes. This is one of the first works of applying deep learning to learn the chemistry of materials. Here, what we did was to take a material like ferric oxide here, if you remember Fe2O3. If you want to build an AI model to predict a property, we need to first have features, right? We need to represent it. And one way to represent is to get these kind of library of attributes like average atomic mass, average atomic number, average electronegativity. All these this kind of vector can serve as a representation. And that's like adding composition based information into the model, because there is something called valency. If you remember, NaCl is valency of +1 -1, KCl is also +1 -1. So if I have NaCl in the model, it will be easier for the model to predict KCl because it has similar valencies. So that's what this will let you do. Similarly, we can do structure-based models where you quantify the structure around an atom and get features from that. But as computer scientists, we were also interested in something diametrically opposite. Let us not give any information, any composition or structure information. Just give it raw fractions. So just give it the fact that it has 2 atoms of iron and 3 atoms of oxygen. That's it. And it doesn't even know what is iron and oxygen. Just it is just columns. So then we found that if we see this error versus training set size, this blue and green curve, these are random forest models using just raw fractions and using we had this 5 minutes, 10 minutes. So here we see that this deep learning model can defeat both the random forest with the raw fraction as well as this domain information. So our deep learning model without this information was able to beat the random forest models with this information, and it also had good properties to extract the convex hulls in unseen data set. And these are some publications where you can get more details. Recently, we added an explainability layer to it. So we found that group 1 and 7 elements, those combinations, it is learning quite well. But group 3 and group 5, it's not learning so well. So that helped us to identify the cause. And then we went back and looked at the data set. We found that at that time, well, this work was done back in 2018. At that time, we did not have much data for this combination. So with newer release of the data set, we see that the model is much better. But this kind of explainability in engineering models is very important, because the cost of false positive is very high. If you have very small data, you take advantage of this deep transfer learning idea, where instead of making a model on the targeted data set directly, we first make a source model and then transfer the knowledge to the target model. And we find that it has very good even extrapolation capabilities. So here the model was trained on this part of the data and tested here. And we can see that the scratch model failed miserably, but the transfer learning model is still much closer to the diagonal. And we got a couple of Nature Communication articles here, which is one of the top journals in this field. Recently, we added a structure-based layer to it. So we get the same kind of trends here. The transfer model is much better than the scratch model. And here we try to evaluate it on more than 100 different data sets to get a similar insight. And then just last year, we added a LLM layer to it. So now instead, in addition to the graph neural networks, we have another head which takes the natural language text of this material and gets an embedding from that, and then concatenates the two. And then interestingly, we found that using explainable AI techniques, that structure information was being paid attention to the most. And this is important because here you can see that we expect that to happen. It's kind of reassuring to see that the model is paying attention to that. This is one of our more recent works in nanocomputers, as I said. So nowadays, our collaborators have a capability to have millions of materials on a small chip, to like 2.5 centimeter by 2.5 centimeter chip. So they cannot scan all the materials manually. So they approached us to see if we can have some AI models for that. And we built two models. One is a nanoparticle image quality check, which is highly accurate and takes less than half a second for each particle. And then a segmentation model, which can reduce the storage speed and the time requirement by more than 25 times. And both of these are published, and there are patents pending on this work. As I said, there is a lot of interest from industry. There is one work from Toyota that I'm allowed to share. There's a lot which is behind the NDAs. But here we build models for magnetic properties, coercivity and remanence with less than 5% prediction error. And that helped them to reduce their waste, so they now perform only relevant experiments, avoid higher-end processing for unpromising candidates, reduce all their SEM man hours and the actual equipment time. And that has led to huge savings, and we can use those savings in turn in the right direction. And I think this is my last example. Just last week, this paper has come out on using large language models for inverse semiconductor design. So using generative AI techniques, we now have this capability of taking just fine-tuning LLM. So here we looked at Tiny Llama, Mistral, Gemma, and the big llama. And here, by fine-tuning that data set, now all we have to do is give it a prompt which says that this is the chemical composition of this compound, and this is the property that I want, and it will fill in the structure for you. And using this technique, we found out of 100,000 candidates, we narrowed down on 6 new semiconductors, out of which we found that at least one of them was both thermodynamically and dynamically stable, with a band gap of around 2 electron volts, which is what is needed for semiconductors, if you guys remember from your high school. So this has just come out last week in Digital Discovery. You're welcome to take a look for more details. This is just a laundry list of all the forward PSPP models, inverse models, structure characterization, and review articles in this field that we have over the last decade or so. As I said, I've color-coded these CS publications in red and domain publications in green. There are also a lot of open source web tools and code available if you're interested. I don't know if it's connected here. Um, okay, I think it's not working here. But yeah, if you go to on this tool, there are a lot of web tools like this. You can put a material of your choice, and it'll give you the predictions of the property of that material with uncertainty. As I said, uncertain quantification, explainability is very important for science and engineering applications, because many applications it's not a big deal. Like, so when you, let's say, purchase something from Amazon, you get an email that you might also be interested in this. So even if it's a false positive, it's not a big deal. You can just delete that email. But in science and engineering, false positive is a huge cost. You cannot make a bridge out of a steel, which the model thinks is good, but actually it's not good. So these uncertain quantification of this property is very important, and that's what we have in this tool that you can try. And I'd like to end with this: that although AI, machine learning, and all this is very popular, very hot nowadays. Everyone wants to get into it, and they're doing this. But I think it's important to remember that artificial intelligence is artificial intelligence. It's not natural. So it's important for us to be able to understand how these techniques are being applied, and because it's very very easy to misapply them. You can see here, it is more often misapplied, either not only by choice. It's easy to misapply even inadvertently. So different kinds of biases can creep in, overfitting, all these kind of problems are very easy. And that's what I tell all my students, that if you're interested in this field, it's just like any other science. You have to learn it thoroughly. You have to invest the time. You have to understand the strengths and limitations, the assumptions behind these techniques, the distributions that each of these techniques are taking in, and so on, so that you can apply them correctly and not misapply them. So I think I'm short of time, so I will stop here, and I'll thank you for attention. Take any questions. Okay. If there are no questions, feel free to reach out at my email. Uh, uh. Thank you, and all the best.
Thank you, Dr. Agarwal, for such valuable insights. Our fourth keynote speaker is Professor Dr. Hussein Mahdi, a lecturer in the Department of Computer and Software Engineering, College of Engineering, University of Diyala, Iraq. He holds a PhD from the National University of Malaysia and an MSc from the University of Technology, Baghdad. He has held numerous leadership roles within IEEE Region 10, PES, IAS, HAC, and Smart Villages committees, and currently serves as a chair of the IEEE PES Humanitarian Activities Committee. His contributions have been recognized with several prestigious awards, including the IEEE MGA Young Professional Achievement Award and the IEEE PES Young Professionals Hall of Fame Award, along with multiple students and leadership awards from IEEE Malaysia and UKM.
Good morning, everyone.
Hello, sir. It's really good to see you over here. You may
Thank
start
you
with the
very much.
session.
Okay, my screen is clear.
Yes, it is.
Hello.
Hello.
Okay.
Hello. Yes, sir, it is visible.
Okay, thank you very much, and good morning, everyone. I really appreciate the invitation from my friend Prof. Shilpa Sharma, and also the Emmett University for the invitation to attend the 16th International Conference on Cloud Computing and Data Science and Engineering. My talk will be bridging the gap between AI and the service of humanity. As I noticed in this conference, the first honorable speaker, I think the previous first and second speaker talk about AI. One of them, it's like how you can use AI for publication in academic way. The second speaker talk about the industry, how we can use the AI for industry application. Now I will take the AI for the third area, how we can use the AI to make real impact in local community, how we can serve and use the AI for the benefit of humanity. My name is Dr. Hussein Mahdi. I am the head of Computer Engineering, College of Engineering, University of Diyala. Also, I am the Power Energy Society Humanitarian Technology Chairperson for 2025, Award Board Committee 2025, IEEE Humanitarian Technology Project Monitoring Subcommittee 2025, and I am also the Vice Chairman of Culture Relation Committee at Iraqi Engineering Union. First of all, I will divide my presentation in two parts. One of them, I will talk about a humanitarian, then about AI and how we use AI for humanitarian project. IEEE, because I work in IEEE, and we are really support all humanitarian technology in our governor board. I will mention about IEEE mission and vision. Our mission, the core purpose of IEEE, to foster technology, innovation, and excellence for the benefit of humanity, and also the vision of IEEE, how we can essential the global technical community and technical professional everywhere connected to each other and try to make real impact. IEEE have a lot of visible impact. Like now we have 5,000 members around the global, 500,000 around the global. We have 39 technical society. We are already have IEEE section in 160 countries. We have more than 1,600 annual conference. We have 5 million technical documents that can all researchers we use. And also we have more than 200 top cited journal, and the most important 1,200 active standard that all industry company they can use. Here we can see some technical society, and I'm sure you will fit with one of these society. According to the subject of today, AI, that means computer society, it will be the most appropriate society for you to join. As organization innovate with IEEE, like you can see here in this slide, we are an all top 5 communication equipment company, also 8 of top 10 telecommunication company, computer hardware, semiconductor company. Like, okay, I want to mention one thing about semiconductor company. We have something we call IEEE award. We provide the best innovation in the world, and the prize will be $2 million. Last year, 2025, the winner, Henry Samuel, I think majority of you hear about his name because he is the CEO of a Broadcom company, and he provide a lot of semiconductor solution and make us use it like for smart cities, IoT system. And the second winner for 2026 also Jensen Huang, the CEO of Nevada company. Also, I think majority of you hear about his name. The word benefit of IEEE information. because we have huge library, IEEE journal, transaction, magazine, conference, standard. Also we have IEEE education course, online courses, and also ebook collection. Now we can just go to deep inside of our speech about introduction to IEEE humanitarian technology, why and how we can apply our professional engineering skills in local community to make some real impact or visible impact. Okay, because like example, Hussein Mehdi work in region 10 in Malaysia, now in region 8 in Iraq. To be honest, I cannot understand what the local community problem that they face in like some places, India, Sri Lanka, Thailand, any country in this region. The best person who can recognize the problem and define the problem, the engineering in the field. Therefore, I encourage all of you to come out with some local community problem, provide some economic, scientific, and also sustainable solution for it. And IEEE can provide for you two issues, monitoring and also fund. Who we are IEEE Teach for Social Impact Hub. IEEE Humanitarian Technology is, have several programs and initiatives supported by a global network of volunteers. We cannot work without IEEE active volunteer, across the global and technical professional working together. We always talk about IEEE as a big professional family, working together to apply technology to solve the world's most pressing problem. We focus about scientific type of humanitarian work. Should be connect our professional skills, engineering skills with the humanitarian impact. Teach for good, technology for the social impact, which makes sense as we are powered by the world's largest engineering network. And according to all the information, majority of the innovation around the world in last 2 decades is related with engineering. Therefore, I think you are the power behind the innovation and the power behind making the world best place to live. IEEE humanitarian technology have, like what I mentioned, have several program. You can see here EPICS in engineering. This is engineering project for community servicing, empowering million life. IEEE site, IEEE special interesting group in humanitarian technology. Also, we have a program we call disaster relief outreach. This is program designed and for American community. And the good thing and the good news, now first time in region 10, it's happened in India. Congratulations to invent in this program. Also, IEEE Teach for Good, and this program really close to me because I work with this program, this committee for last 5 years. IEEE Smart Village, and this is have a huge impact in different country, different regions, especially in Africa, and also IEEE REACH program. And by the way, each program have different kind of fund and have different kind of criteria how we can provide for you. Now I think we can understand that IEEE as non-profit organization try to help the local community by the engineering from the local community itself. Therefore, I encourage all of you to be engaged with IEEE because I totally believe all engineering have, amazing idea, creative thinking. Therefore, have, a lot of solution, technical solution for the problem that face the local community. But sometimes they have leaking of fund or how can start in the initial start the project itself in local community. Because to be honest, sometimes we need to encourage our engineering to take the lead in local community and make the change. I talk about IEEE Teach for Good program because I told you I am part from it. We provide funding opportunity to support grassroots technological project led by IEEE member that address the local change related to sustainable development, just sustainable development goals. And each project have fund from 10 1,000 to 10,000 American dollar for 1 year period. And for sure, because it's very short time, if you have any information, you can just reach out for me and provide for you the criteria, how you can apply, what we need to do in your project to have fun, all this kind of issues. Teach of Good 2025 highlight point what we did and what is our impact in 2025 as a program. We have more than 300, almost 400 applications have been submitted across 6 schools in 2025. We provide fund almost 340,000 American dollar for 40 projects in just 2025. And the good thing, the amazing and potential volunteer from IEEE Region 10 got the most of the support. We have 240 applications received from Teach for Good open call, and 26 were approved for funding. That means from 40 projects, we have a 26 project just from Region 10. And India take the lead in this funding opportunity and get the most of fund from Teach for Good in 2025. I think you can see here, this is the email coming from IEEE Humanitarian Technology Board in end of this year to show us our impact across the global. Okay, all of us engineering, we learn a lot of skills, but the value of our, ourselves, the value of the reflecting the value of ourselves, how we can make the real impact in the world, not just have knowledge, not just publication, not just create what we call innovation or make patent. How we can use this knowledge, how we can change the research to be applied in real world, how we can apply the innovation, how we can apply the patent in real world and make benefit for local community. Here, according to the statistic in 2025 for all the fund for humanitarian technology, how much providing fund, you can see here we funded almost 100 funded project. We spent almost 1,003,000 American dollar in 2025. Our project affected almost 370 person, like one project in each area, like affect like 200 to 300 person. That the total of our people take advantage of from the project that already done by IEEE engineering volunteer in a local area, almost 370 people, individual people. Why we need to encourage the engineering, and also why we do this effort, because engineering and technical professional has a unique ability to shape the future and create sustainable solution for the world most pressing challenge, engineering with purpose. We are trying to change this engineering skills to real project in local community and try to measure the impact of this project. We'll try to convert the equation, the knowledge, to draft project. After draft project, we try to see the implementation design phase by phase and support you financial and technical. Now we talk about the AI. I think our honorable speaker explained what is the AI already, but how we can use it in a humanitarian technology. We know the AI, it's include all the section of our life. We know the importance of AI, but how we can make the AI change the people's life in reality. Okay, exploring how artificial intelligence is transforming our world and shaping the future of human progress. The promising and stack of AI to be honest, in human life, transfer every sector. It's related with healthcare, disaster response, sorry, climate change action, and education. That means AI touch the billion of life across the world, and also responsible deployment. It is very important issue. AI benefit reach all the communities, which actively preventing bias. Also, it's need to have some rules to follow, because AI, it is a huge technology and it is very fast developed. Therefore, we need to put some ethical rules for it. Today challenge, it is most important how we can apply AI in all this technology without affecting about our human ethics and the fundamental human value. AI is saving the life. This is, I think, this is common sentence. Everyone know or know that AI affect about human life through healthcare, disaster response, like example, early cancer detection, disaster forecasting, like floods, earthquake, fire, climate change, all this disaster. And we will take, one case study. It's nearby my country to explain how AI, take real action to save the life. And also AI, it is very useful for, search and rescue operation. Fighting climate change is one of very important, because climate change is a global, I think it is red sign of our earth, about what's happened, about what the human action.
I
Okay.
apologize to interrupt, sir, but we are short on time, so can we please wind it up in 5 minutes?
I think we have 45 minutes my speech, or okay, okay, it's okay. AI Okay, AI also can use a renewable energy optimization, environmental also monitoring, policy guidance, and also in education and the human right. And we can see the online education and also AI education tools that is already very useful, especially like during the crisis, like Corona, like effect example. And also we can use it in different section to motivate and give motivation for the student to learn. And also like AI tools like for lab, how we can make some experience in some AI tools without make it in real, saving time, saving cost, reduce the risk. And also like example, I want to, because I want to see one real example how I helped in disaster relief management and or disaster response. There is some earthquake happening in Turkey 2023, and it's really have a huge impact. Like it's the magnitude of earthquake 7.8, and also we lose 42,000 life during this disaster. And also the damage cover almost 50,000 square kilometer in Turkey. How AI help us to scale and measure the disaster response. We check the collapse in all the infrastructure, and also time critical rescue, divide the rescue team according to the disaster effect, the disaster area effect, and also communication breakdown, that AI help us to communicate with all the rescue team, all the people survived from this disaster. Also, AI, powered by satellite damage assistant, help us to development phase, rapid development, and also mission support, acceleration response, to help the stakeholder to take the correct decision. And also community-driven teach innovation, help the people in open source platforms, social media, to like example, to sign, he is safe, he is in this place, WhatsApp helpline, all this social media also help us to rescue the people. Digital tool for safety and support. We have different, digital tool to support AI to support the safety of the people in disaster area. Now the lesson we learn from Turkey disaster, we need technology and also AI true strength for for disaster response and integration in essential. We need to build an AI system to mitigate and also to predict what happen in the future. This photo with IEEE president in last conference happened in Tokyo. It is about IEEE Region 10 humanitarian technology, how we can use the AI for the disaster response. Okay. Thank you very much for your attention. And if you have any question, I am ready to answer. And also you can reach me or communicate with me. Here, my contact information, my email address, my WhatsApp number. If you have any question or you need any help or support to apply for funding opportunity, how to use the engineering skills for the benefit of local community. Thank you very much.
Thank you, Dr. Mahdi, for enriching us with your perspectives. At Amity, you may stop sharing the screen, please.
Okay.
At Amity, we believe in long-time associations with our collaborators, and this is the time to offer them a memento as token of appreciation and a lasting memory. May I invite Dr. Shweta Srivastav to present a memento along with certificate of guest of honor as well as contributor as a keynote speaker to Dr. Ramzi A. Harati. Please give a big round of applause. Please give a big round of applause, everyone. Now I would like Dr. Shweta Srivastav to present a memento and certificate of honor along with the certificate of keynote presenter to our esteemed speaker, Professor Dr. Ankit Agarwal. Let's have a big round of applause, guys. Please going. I would like to thank all of the panelists for being present here, taking out their precious time to make this a memorable event.
With this, we conclude the session. We hope that it was an enriching and informative experience for everyone. On behalf of Amit University, Uttar Pradesh, I extend my heartfelt gratitude to our esteemed keynote speakers for their time, effort, and valuable insights, and to all the faculty coordinators for their constant support and guidance in making this event successful. To all the participants, thank you for being part of this session with such enthusiasm. Wisdom is not a product of schooling, but of the lifetime attempt to acquire it. Let us carry forward this idea, sparked here into our research and innovations. Thank you, everyone.